All right. So, okay, first, I guess we're just going to review the basics of matrix stuff. I'm going to go pretty fast through all of this because I assume you at least watched the class lecture or the finite show or skimmed the book or something. But if you have questions, just stop me. Okay, so just some basics for like vocabulary essentially is this first section of stuff. Dimensions of a matrix, it always goes rows first, then columns. So if I had a matrix like this where I had stuff, I would have 2 rows and 3 columns. So this is how I'll be writing my dimensions of matrices. Okay, entry I comma j is the entry in row I and column j. Melanin talked a lot about like the ith and jth stuff. I don't really do that. I'm going to try to keep an eye out and see if that's going to be common this year, but it hasn't been in the past. But as an example, if this is matrix A, and matrices always have an uppercase letter assigned to them, it'll never be like a lowercase letter. If I wanted to know the entry matrix A and then 2 comma 1, if I is the row, so I is the 2, I want row 2, so I'm down here. And then J is the column, so 1 is my column. Those overlap in this entry right here. So whatever entry there would go for A21. So that might be used, honestly, it'd just be to, like on a test kind of stuff, be like, what is the entry in this entry of the matrix? Because they can't ask you to like fill out a whole matrix usually. I don't know if they're going to figure that out this year, but last year they didn't have that figured out. So they used this kind of notation to specify where they wanted you to find a number and plug it in. All right, so row vectors, column vectors, it's just a matrix, either one row or one column. If you took like a beginner physics class, a vector is like an arrow. So think of it like that, like it's just the one either row or column. Some professors use those as words to teach things like matrix multiplication, but otherwise they're not very important. Next we have zero matrix, which I've never seen used before, but it's just a matrix with all zeros. It's in the book, I think, but pretty self-explanatory. Also, I've never seen it used. But this identity matrix is important, and hopefully we've been hitting this concept for a long time in class, so you should get that one now. It's just a matrix with ones in the main diagonal and zeros everywhere else. So by definition, an identity matrix must be square. So it can be like a 2 by 2, 3 by 3, 4 by 4, anything square. And square just means it has the same number of rows and columns. So it literally makes a square. And then if I wanted to do like a 2 by 2 identity matrix, you put your ones in the main diagonal and zeros everywhere else. 3 by 3, same thing. Ones in the main diagonal and zeros everywhere else. So this gets used a lot. And then I think Melanin had a notation for how to call these. I've seen this before, or it's the identity. So identity is always an uppercase I. And like a 3 would be a 3 by 3. I think he had a different way of notating a 3 by 3 identity matrix, but they're all meaning this. So is there any questions with this vocabulary? All right. Thank you for the thumbs up, Matt. Cool. Okay. Matrix addition and subtraction. Essentially, It's important they have to be the same dimensions, but you just subtract corresponding entries. Do you guys want an example of this? No. Okay. All right. You can always Google it and watch Khan Academy if you want to. Scalar multiplication is also quite easy. It's multiplying a matrix by a constant, and essentially you distribute the constant. So if I had a matrix like this, I can take, I don't know, any number out here, multiply it by a matrix, and then just distribute that 1/2. So it would be this. So it's just called scalar because you're technically, or I guess in English, you're scaling the matrix. So this scaled it down by 1/2. If I wanted to scale it up by a 3, factor of 3, I would take 3 times my matrix. So that's why it's called a scalar multiplication. Okay, next we have matrix multiplication, which is in those. I might do examples and then come back to matrix multiplication, or just skip these examples and do a multiplication problem. I'll take a vote. You can do the vote in chat or whatever you want. I don't care. Speak up, whatever. Do you guys want me to do either of these problems? I'll let you read them if you don't. I think you're all in, Melanie. And yes, please, 4. Okay. And then I know Mia had a question about like this. So I'll touch on that. We can look at 4 real quick too. Okay, so I liked 4 as a question because it has variables in it, which means you cannot just use a calculator. I'll show you the calculator I use later. It's great. But here you wouldn't be able to use it because it can't handle variables. So for these problems, and I've seen a few other ones written that are similar, essentially think of it as any other problem with 2 variables that you need to solve for. So this one just happens to use matrix algebra to get those equations for those variables. So here we have C times the matrix 2, 5 plus D times the matrix -3, -5 equals -38 and -75. So we have some scalar multiplication going on with this C and D times matrices. And then we have them, added together here. The first thing you'd want to check on a test, if in case one of the answer options is like does not exist, would be, can I even add these 2 together? And to check that, I would say first look at your multiplication. So you need to always follow your orders of operation. So multiplication comes before addition. Your multiplication is just going to be distributing this C into the matrix and distributing the D into the matrix. So it will not change the dimensions of the matrix. So we'll still have a 2 by 1 matrix for both of these pieces. And because they're the same dimensions, that means you can't add them. So you're good there. You'll be able to create a sum of those. So we're good there. We knew you were good, but on a test, you might not. All right, so now we're going to do some scalar multiplication. And think of this to figure out C and D. We already have the end product and sum of this stuff. So think about how to go from here to -38 or to -75. Okay, so if I wanted to figure out how to get -38, let's start on the left. So I would take C, I'm going to distribute the C into this matrix. So I'm going to have 2C and 5C plus sign. And then let's distribute that D into the next matrix. So I'd have -3D and -5D. And that's going to equal my negative 38 over, or sorry, not over, just negative 38 and negative 75. All right, our next step to get from the left side to the right side is just going to be matrix addition. So since the same dimensions, you just take each corresponding entry and add them up. So if I were to take 2c minus or plus a negative 3d, that has to equal negative 38. See where that's coming from? I'm taking this number plus that number to get the product or the sum. Okay. So essentially we now have an equation that looks really familiar. Let's do it again for the next one. So I'm going to take 5c plus a negative 5d, or just minus 5d, equals negative 75. And usually this is the kind of math you would do like in your head or with a calculator or whatever it is. But here, since we have variables, we can take advantage of that process and write equations that use the variables and have equal signs. So now we have what looks like a normal system with two equations and two variables, and then you can solve. Does that make all sense? Any questions there? Thumbs up. Okay. Anyone would want me to work out this math? We've done it quite a bit with the system stuff. All right, got a few no's. Okay. If you're still kind of iffy on this system stuff, what's the answer? Someone says, let me look at my web work real quick. Hang on, there's a lot of stuff in my way. I was gonna say, well, if you're still worried about that kind of stuff, I did it a few days or a few recordings back in Pass. It is 8 and negative 7. I'm pulling it up now. Oh wait, hang on. I flip-flopped them. Negative 7, 8. Yeah, so what Ethan said in the chat was right. D is 8 and C is negative 7. And let me see when I did that. Yeah, so if you're stuck on that kind of stuff, I did it on March 16th, which is the first day after the midterm, apparently. Oh, did I? Wait, hang on. Maybe I didn't. When did I do that, guys? I did it. Okay, well, let's set it up real quick. We'll just set it up. Okay, so if you're going to do a system with two equations like this, you can either do substitution or elimination. And this one, I would probably do elimination, I guess. Neither of them is going to be great. Elimination is just manipulate your equation until you can add them together and cancel a variable out. So if I wanted to take both of them, and I'm just going to take both equations and multiply them by a whole number. So now I have 10c minus 15d equals whatever that is. I don't know. And then this is going to be, so 5 times 2 is 10c minus 10d equals, this is like 150, I guess. Maybe. And then to add them together, I need one of these to be negative. So I'll just make one of them negative. And now I can take my two equations, add them together, and they'll cancel these C's out. So I have negative 5D equals some number. And then divide by negative 5 on both sides. D equals that number divided by negative 5. And then now once you have one of the variables, plug it back into one of your original equations. Either of these two would be fine to get C. And I know I did that somewhere, so I'll find it later. Or you can look for it somewhere. Okay, is that good enough? Yep, cool. Okay. And then let's talk about Mia's question with when you have a bunch of them together. Essentially, you can multiply in any order. It won't matter usually. So for like K down here, this EBA, I can pick either two of those to multiply as long as I don't change the order. So I can take E times B first and then multiply that by A. I can take B times A and then multiply it by E on this side of that. I just can't take E times A. That's illegal. You cannot move around multiplication, which I'll actually not talked about yet, but that's the rule for matrix multiplication. So let's talk about multiplication, because I have not yet today. And then I'll come back and finish doing this out. Okay, so matrix multiplication, where did I have those notes? Here. All right, so we're gonna talk about this real quick. Here it is in English words. I think it's easier to see it done rather than written out, but the most important thing with matrix multiplication is it's not commutative. So I'll type that here. So like a normal anything else, if I want to take 4 times 3 or 3 times 4, that'll get me the same answer. So the normal multiplication is commutative, if you remember that property from like 6th grade. But matrix multiplication is not the same. So if I had, I don't know, A and B, A times B will not equal B times A. So that's the most important thing with matrix multiplication, is you can't move it around. And then in order to even do the multiplication, you have to check this check. So the number of columns in matrix A has to equal the number of rows in matrix B, if you're going to do A times B. So let's do an example of that. And I'm going to go a little bit fast. In person, I can tell if you're confused. I cannot tell if you're confused with Zoom. So just tell me if you're confused, okay? I'm going to do one that has different matrix dimensions instead of the one that he had in his web work. So that check is looking at the dimensions of them. So the first thing you always do is write out your dimensions and check. So dimensions go rows, then columns. So this one has 2 rows by 3 columns. And this one has 3 rows by 2 columns. And the check is that the 2 numbers in the middle, so this and this, have to be the same. Okay, so this is the number of columns in the first matrix. This is the number of rows in the second matrix. and they have to be the same in order for you to do matrix multiplication. If they're not the same, then it's not defined, or however they want to use those words. All right, so now that we know that they're the same, we're good. A good fun fact, and could be helpful in some theory questions, is that the outside two numbers are going to be the dimensions of the product. So this is going to equal a 2 by 2 matrix. So that'll help you with this question as well, is knowing that the outside two numbers equals the dimensions of the product. Does that make sense for the person who asked that question? I don't know why it works, it just works, and I was told that. So if you wanted to prove it, I'm sure you can go find a proof for like much higher level math, but I just take it as I get it. So these two numbers, it won't always be a square matrix. I could have a matrix that was like a 3 by 3 here. These inside numbers will still be the same, so we're good. But then the product is now going to be a 2 by 3. So it won't always be square. It'll just be whatever those dimensions are. All right, so now let's do the multiplication. Okay, so those of you that have seen me in person saw me do my hand movements, and it looks ridiculous, but I swear to God it works. So how this works is for matrix multiplication, and hello Cam, what you're going to have to do is take an entire row.
Sorry to interrupt you,
Yes,
Brooke.
please do.
But I forgot what date this was. Let me check the lecture date in my notes here.
Sure.
I guess it was March 26th that Melanin was going through something. And in his example, when he was just explaining the like single row or single column matrices, the rule of looking at the inner two dimensions was betrayed in his example. So in his example one, he had a 1 by 3 matrix and then a 3 by 1. And then you multiply those together and you get a 1 by 1 matrix. So I was just curious why you use the outer dimensions on those as opposed to the inner dimensions.
That's a great question. Honestly, I don't think I've ever done one of these, except actually there is a term for this. Okay, so the reason why this works differently is because this like vector multiplication is what you use in matrix multiplication, except we kind of skip this part usually and teach it as matrix multiplication with a bunch of steps in between. So that's true. So this would be like a vector multiplication. I probably should just type that. Vector multiplication. So it's two different vectors, and it was set up like this, right? With the row and then the
Right.
I guess it's a 1. Well, this still works. It's a 1 by 3. This is a 3 by 1. So my inner numbers are the same, which means I can do the multiplication. And then my outer numbers means I'm going to get a 1 by 1, or essentially just a number as the product.
Okay, so it's only whenever it's single vectors, I guess, that that this would apply then, right? Or I guess it still follows the same rule. It's just that you get the matrix dimensions from the outer two then.
Yep.
Right?
It still follows the same rule. So you still have to have the same number on the inside, whether it's vectors or if it's larger matrices, and you still get a product that has the dimensions of the outer numbers.
Okay, I see.
Here we got a 2 by 2.
Something about it just confused me, I guess, the day that he was giving these notes, but now I understand it.
Okay, good. Glad you asked. Okay, good to clarify, because I'm sure everyone else is also like, I wrote this down in class. I don't know why. So glad you asked. But yeah, we'll be basically doing vector multiplication within matrix multiplication. Some teachers teach it like that. I've found most students don't prefer it the other way that I teach it, but either way would be fine. if you liked his way of teaching it too. Okay, so I'm gonna erase this. I'll leave that up though. Okay, so let's do this problem, which is larger than just one of these. Actually, since I have it up, we'll do this problem. Okay, so I'm going to do it with variables in it, and this is why it's important to learn matrix multiplication, because they can easily throw you a problem that looks exactly like this and say, hey, what's this going to be? I don't think they will because it's a lot of variables, but it's easy to plug in a variable anywhere in a matrix and have you multiply them together. So you'll still want to be able to do it by hand in case they do that on the test. So we can do this one first. So if I had these two matrices, we already checked if we can even do the multiplication. The inner numbers were both 3, so that means we're good. And we know that the outer numbers were both 1, which means we're going to have a 1 by 1 as our answer out here. How this works is you take the entire row by the entire column. And I think I'm mirrored on my Zoom video, so I apologize for that. I don't know which way goes which, but the row you multiply across left to right, which for me is this way, and then the column down. So first, you take the first one from the row times the first one from the column. So it'll be A times D. Then you move down. You can take them, oh, it's hard to see. Take the middle ones. So you'd have plus B times E. And then you add the last ones. C times F. And the reason why I do this is because as I'm doing it, I move my left hand left to right across that row, and then my right hand top to bottom on that column. So it kind of helps you do it in your head eventually, of making sure you multiply the same numbers together as you go down it. So that's why I do this hand thing, and I'll be doing it all day. So does this make sense? Okay. Awesome, good. What does that mean with the first? Whoever asked the question about outer numbers, the first and last, if you're referring to like this and this, yes, I call those the outer numbers. So here we have a 2 by 2 as the product. Okay, so let's, and I'll actually scoot this over so you can keep referring to it if you'd like. All right. So for this one, it's going to look huge, but eventually you'll be able to do it in your head, I promise. So if I wanted to take my product and look for this first entry. So if I were going to have, I'm just going to give myself a lot of space in here. Here is a 2 by 2 matrix. It'll have numbers like, I don't know, these are random, but it's a 2 by 2, just elongated. So if I'm looking for this first entry, this is in the first row and the first column of my product. So you take the row from the first matrix, and you take the column from the second matrix. So first row, first column, first column. And now you do what we did with the vector, number by number. So 1 times 3, let me give myself my space back. Plus, move down 1, 0 times 1, plus, move down again, 2 times 1. And now we've hit the end of our row and end of our column. So that is the entry in that spot of the product. All right. And just stop me if you need me to slow down or reiterate, color code more, anything. All right, you can do any of the entries next, doesn't matter. I'll go and do this one over here. So we're still in the first row of the product, but now we're going to be in the second column of the product. So that means I'm going to take the first row of the first matrix and then the second column from the other matrix, and then multiply. So I got 1 times 1, 0 times 2, and 2 times 4. So that's the entry in that spot of the product. All right. Should I keep going with the other two entries, or should we just simplify? Yes, okay. All right, so let's say I wanted to figure out this slot right here. Which row and which column do I want? I'll have someone answer me.
Second row, first column.
Second row, row 2, column 1. So you get your row from the first matrix, and you get your column from the second matrix. So if you're someone that likes words written out, you can write that down. I'm sure you can write it better than I'm going to type right now, but row from first matrix, column from second matrix, and then the rest of the steps. Okay, and I'll color code this one out like we did up here. So we know we're going to be using that row in this column. I'll just box them out. Okay, so 3 and 3. So 3 times 3. And then this is my thing I move. I guess it might be like this way. I don't know. And then that was this portion. Next is taking 1 times 1. And that's this portion. And then our last portion is taking 4 times 1. And that is that entry of the product. Okay, what row and what column do I need for this one? Two and 2, someone says. Yep, so this isn't the second row and the second column of the product. So I'm taking the second row from the first matrix. And this time, I'm taking the second column of the second matrix. All right, so my first piece, 3 times 1. Next, we got 1 times 2. And then we've got 4 times 4. And then we're done. Okay, does that make sense? Yes. And if it doesn't, ask a question or say help. We can redo it. Okay, so I'm just gonna simplify this down. So this number is 1 times 3 is 3 plus 0 plus 2. So that's gonna be a 5. This one's 1 times 1 is 1, plus 0 times 2 is 0, plus 2 times 4 is 8. So 1 plus 8 is 9. Here I've got 3 times 3 is 9, plus 1, plus 4, so 14. And this is 3 times 1 is 3, plus 1 times 2 is 2, plus 4 times 4 is 16. So 16 plus 2 is 18, plus 3 is 21. So these two multiplied together equals this. All right, how are we feeling? Confident? Okay, or like lost, or thumbs up's good. Pretty good. Okay. All right, great. I'm going to show you the matrix calculator because it is way faster if you have numbers. You can literally Google matrix calculator. I think this is the first one that pops up, matrixcalc.org. And I like it because it's easy and simple and it has everything I want. So you can just type in your matrix and then your other matrix. 2, 1, 4. Let's see here, I have matrix A and matrix B, and then they have operations in the middle. If I tried to add them, essentially it has to be the same size, and size is dimensions. But I can multiply them, and it shows up down here. It's 5, 9, 14, 21, which is the same thing as we got right there. So this is easy. If you are on a test and you do have full numbers that you can use, I would say use a calculator because it saves you time. But I still would say you need to know how to do it by hand. All right, here's a proof of why you can't flip flop and move around stuff. So if this is A and this is B, so I did A times B right here, and that got me this. If I wanted to do B times A, where did my thing go? This button will flip flop A and B, so you see they just kind of flip flop back and forth. If I tried to do it now, you can still do it, but it's giving me a 3 by 3. So here's the one that we just did, if you flip flop them, versus the one we did by hand. So you can see that they're very, very different answers, which is why it's important to not flip flop and move around any matrix multiplication, because we get different answers. All right, how are we doing? It's 6:40. I want to get through a lot more than this, but I also don't want to blow your reins and make them make you guys like overheat. So, okay. I'm gonna save this problem for a different day. And let's talk about inverses. All right, quick brain break. Take a drink of water, whatever you need. We're gonna do inverses. And then we should be good. Oh, hang on, I was gonna be back to this problem with this. Okay, so let's do one of these just to test the dimensions stuff. So if I'm going to take E times B times A, I can take either one I want first. If I wanted to do E times B, I can look at, it says E is a 2 by 2. So we're going to do E times B. E is a 2 by 2. B is a 3 by 2. Our check is if the two middle numbers are the same. These are not the same. So I cannot take E times B. And I don't know if every single case you can throw out the whole thing at this point. I would still personally check the other one just because I don't know the math behind that. but it usually does not work. So I'll just try the other side of it just in case. B times A. So B is a 3/2 again. A is a 2/2. Oh, this might work actually. So if A is a 2/2 and B is a 3/2, let's check those inner numbers. Those are the same. So I can do B times A.
Hey, Brooke.
Yep.
A is a 2/3 or something like that. Or
Oh,
yeah,
that makes sense. Okay, thank you.
You're welcome.
Well, here, if it was a 2/2, it would have worked. Apparently A is not a 2/2. Okay, backing it up. A is a 2/3. Is that right now? A 2/3. So we still have, yeah, you can still do B times A. Okay, so if B times A is going to give me a 3/3, so I'm going to call it BA, is a 3/3. And then I wanted to multiply this E as well. I need to make sure the E is to the left side of the BA. If the E was on the right side of the BA, I've now moved it over here, and that's not allowed. So I just need to make sure whenever I do this kind of stuff, I make sure I keep it in the right order. So E was E a 2/2. And as you can see here, these inner numbers are different, which means I cannot take E times BA. So this whole thing is not going to be defined. Does that make sense? Yes.
I have a question.
Yeah.
Why did you just pick EBA out of all of those?
Because Mia asked earlier about what to do when you have three things multiplied together.
Oh, okay. So what does it even mean by following matrix? Which of the following are defined?
Okay, yeah, this is a crazy question. So what you have to do is look at each one of these and test if it's going to be possible. So we can, I would start it here.
So you literally have to do all of those. What? All right.
I would do it once in my head kind of first, go through it and see if I can get it right. If I get it wrong,
Okay.
come back and do it again. On a test, it won't be this long. It might be a couple of these and say which of these are not defined or are defined. You'll get like 1 out of the 4. But
Okay. Thank you.
yeah.
There's one on the next WebWork, like WebWork 27, that's kind of like this. It's like really long and stupid.
Yeah, that one was annoying. Good practice of moving things around and multiplying, but they're long. Sorry.
Gross.
Yep, sucks. Is what it is. All right. Essentially, as long as they're columns from the first. Yes, that is correct for the person that DM'd me that. Okay. 15 minutes of inverses. Okay, so matrix division does not exist. You can never divide matrices by each other. What you can do is matrix inverses. They're not the same, but they're like sorta, not really, but never do matrix division, doesn't exist. Okay, so inverses as a term, you're very familiar with these. You might not know it. If I had the fraction 4/3, so 4/3, the inverse is just flipping it. So 4/3 and 3/4 are inverses of each other. And the mathematical definition of inverses is that if you multiply them together, they equal 1. So 4/3 times 3/4 is going to be 12/12, which equals 1. So inverses, when multiplied together, equal 1. Same thing with matrices. In the matrix universe, the identity matrix, if you remember that guy from the very beginning of today, is kind of like a 1. So that's an identity matrix. That's a 2x2 identity, kind of like a 1. So if I had a matrix A, times the inverse, which is denoted by this -1 superscript. So this is A times A inverse. If they are indeed inverses of each other, they will multiply to equal the identity. So that's like the mathematical definition of them. This, you don't really use it usually. It's occasionally good for like that problem that Mia is talking about at the end of Weber 27. We'll use it later today too. It's good for theory kind of based stuff, or for algebra where you're like moving things around like this. Or it's good for checking if they're inverses or not. So that's the mathematical stuff that's sometimes helpful. Let's figure out how to find an inverse just given a normal matrix like A. You have two ways to do it. One way is to create an augmented matrix, which is just a matrix that has that bar in the middle of it with your matrix on one side, the identity on the other side, and then you row reduce it. So if I wanted to find the inverse of a matrix, and I'm going to test one out real quick in my calculator just to make sure it exists before I do it. Okay, not beautiful, but fine. Okay, so if I have the matrix, I'll call it, I don't know, N. I have 3, 1, 1, 2. I was given this matrix N and asked what is the inverse of N. One strategy is to create an augmented matrix with the identity. So I would take N, just 3, 1, 1, 2, and slap on the identity with it. So it'll look like that. And then you will row reduce this side all the way down. So if you remember row reduction, the goal is essentially to turn it into this kind of thing with like the leading ones and the zeros. So that's how you will do this. So I'll just do the first step and then move on and say I don't have a lot of time here. But if I wanted to find the inverse of this, my first thing is to get a leading one. I would either divide by 3 or flip the rows. I'll just divide by 3 because that's like the usual thing you do. So I would have 1, 1/3, my line, 1/3, 0. I'll leave this row alone. Next, I need to take my leading one and use it to turn the column into zeros. So I may take row 2 minus row 1, which I'm going to move it down here. Copy row 1. Oh. And then subtract them from each other. So 1 minus 1 is 0. 2 minus 1/3 is going to be 5/3. 0 minus 1/3 is -1/3. 1 minus 0 is 1. And then you keep going until this column also looks like the identity matrix. And what you'll find is that this is going to start turning into other numbers. And those other numbers are its inverse. So these will keep changing until this side, which originally started out as the identity, will become the inverse. So that's the one way to do it. It works for any dimensions as long as it's a square. It's just kind of tedious. It is also in the calculator. So I plugged in the matrix, pressed find the inverse, and it gave me the inverse. Okay. Strategy 2, if you have a 2x2 matrix, you have a shortcut formula. And I did not write that down, so let me write that down. Okay, so I'm gonna keep using this like A, B, C, D. That's pretty standard. And the shortcut, oh, actually, I meant to write right there. The shortcut is 1 over A times D minus B times C times flip D and A, make B and C negative. All right, so this is the shortcut. If I wanted to, I'll use this N again. Okay,
And
so
does the shortcut be done for any other size matrices or no?
they exist. They're just real beefy and not honestly a time saver. If you had to do it row reduce or find the inverse of a 3x3 and you weren't able to use a calculator, then I would honestly do this. The equation for that includes this. It'd be 1 over that. And then also a bunch of random stuff in there.
Gotcha.
And it's not fun. So I would honestly row reduce if I had to. If I could, I would use a calculator. They don't make you do it usually, but sometimes. So here we have a 2x2 though, so the shortcut's small, which is nice. So if I wanted to find n inverse, I would take 1 over a times d, 3 times 2 is 6, minus b times c, 1 times 1 is 1. Flip a and d, make b and c negative, and then simplify. So it's going to be 1 over 5 times that guy, and then I would just distribute that 1/5 to get my answer. So for time's sake, I'm not going to do the math all the way out. But you'd have, I can say, well, 2 over 5, negative 1 over 5, negative 1 over 5, 3 over 5. So this is the inverse of n. So that's why the shortcut's so much nicer. Or use a calculator. Okay, I got 5 minutes. Questions? Need a breather?
Do you have time to do like the second part of the problem right there?
Yep,
'Cause I
I will.
how to do the inverse, how to find the inverse, but I don't understand how he's like applying it to crap. Just don't make sense.
Yep, we will definitely. That's the goal. Okay, so find the inverse of A. I was going to ask y'all if you want me to row reduce that. I'm not going to because time. So instead, I'm plugging it in here. So negative 1, 1, 2, 1, 0, 2, negative 1, 1, 3. Press find the inverse. It'll pop up down here. And I'll copy that over. And if I'm using the calculator, I always check to make sure I typed it in right, just in case, because that kind of error would be really annoying on a test. Yep, okay. I pressed find the inverse, and that was good. All right, so this is going to be 2, 1, negative 2, 5, 1, negative 4, negative 1, 0, 1. Okay, now it says solve for x, and our equation is a times x equals that. So I think it looks kind of harder because it's all squished in here. We're solving for x in this. And it's basically like back to algebra. So take out the matrix stuff for a minute. Think about algebra. If I wanted to do a times x equals, I don't know, 3, and find x, I could divide by a on both sides or whatever. Or I can take 1 over a times a, because this is going to cancel to be 1. And I could take that on both sides, because on an equation, you have to do it to both sides. This is going to be a 1, because it's going to be a over a. Copy my x equals, and then we have now 1 over a times 3. We're doing the same thing, except with matrices. All right, so same thing. We multiply by an inverse to isolate the x. And what's really important is to watch the direction where you're doing it. So because a is to the left of x, I'm going to multiply this thing to the left. Because now, like that example with like the EBA, I have essentially, it's all multiplication. So there's no like distribution or anything. I just have a inverse times a times x. I know that this is going to equal 1, or the identity matrix. And I guess I should mention another cool theory thing. So I'm going to have technically the identity times x. And here's a matrix rule. And I have these written out nicely somewhere else to show you too. Anything multiplied by the identity is itself. So x times I is going to be x. And you can flip-flop it, whatever you want. Anything by the identity is itself. So we're going to have just x on this side. On the right side, whatever I do to one side of the equation, I have to do to the other side of the equation. So I have to do it to the left side of this part of it too. I can't take this and do it on the right side, because as we know, matrix multiplication is not commutative. So this is not correct. You need to do it to the left side of that, because you did it to the left side over here. Okay, so that's that. I now have x equals something. A inverse is a 3 by 3. This is a 3 by 1. My inner numbers are good, so that means I can do it. And I'm going to get a 3 by 1, which, as you can see here, is x. And I'm going to plug that into a calculator.
Where did we find a 3 by 3 from?
A inverse of A, right here, is a 3 by 3.
Oh, I'm sorry. I didn't know these problems were connected. That's why I was confused.
Oh, yeah, it's like a two-parter. So I'm just going to copy my A inverse just so it's a bit clearer to see. Kind of messily, but you get the idea. -1, 0, 1. So here's my A inverse that we found earlier. And then I'm multiplying that by, I was copying it down by what they gave me in that equation earlier. 3 by 3, 3 by 1. You can multiply them together, and it will give you x. So we'll just do it right here real quick. Clean that out.
Can that be a -3 on the bottom of the?
Oh, did I mess? Oh, yes, thank you. Good catch. Copy errors all over the place. This one's a 3.
Oh, I wasn't even talking about that one. I was talking about the one in red.
Wait, hang on. Oh, no, you're right. I was right. Hang on. Wait, back up. Did not have a copy error. The one on the right. -3, you're saying. Yes.
Yeah.
This is the copy error. Thank you, Ethan. Okay, so we're good. I'll double check my inverse just to make sure. So this is A. I asked for the inverse to get 2, which you can see it. 2, 1, -2, 5, 1, -4, -1, 0, 1. Yep, that looks good. This is nice because I can insert it into one of these. I'm going to insert into A. And you can see up here, it'll flip or it'll change. So now I have my inverse in there. And then I'm going to put in this guy in red over here. Say A times B. And here's my answer. So X is going to equal 0, -3, 0, which is correct. I checked it earlier. So that's how to do that one. 0, -3, 0. I think phi was basically the same exact thing. Okay, questions? You guys feeling okay? Or just mind wiped?
A little bit of both, but thank you. Thank you
Okay.
so much. Have a nice night.
Yeah, you guys too. Yeah, I'm going to save the rest of this for next time, but that was helpful.
Thank you loads, Brooke.
You're very welcome. Have a good night.
Thanks
Enjoy the
again,
rest of
Brooke.
your night.
Thanks.